Welcome back, everybody. So I just wanted to give you some quick messages first about the topic today. So on Monday, we started to look at this two-body scattering case. And this is something which we will not study in exercises. You will not encounter this in the final as well. But this is something for further studies. And you're going to meet this kind of way of thinking and usage of the two-body scattering problem. So I'm just going to wrap up in the first 10 minutes today. I'm going to be a little bit sloppy with the derivations, but I want to give you the final expression and which kind of steps are needed to get there. Then we are going to enter the final topic this semester, which is actually us bringing mathematical beauty to classical mechanics. And the Lagrangian formalism is something you will meet in many, many physics courses, together with something which is called the Hamiltonian formalism. And what you can do now is to derive all the equations of motions which you have seen till now by starting with kinetic energy and potential energy. And that's extremely powerful. So instead of you setting up the forces and then trying to elaborate, oh, this is the acceleration, and these are the equations I have to solve, now you can derive the equations of motion, that means Newton's law, from kinetic energy and potential energy. And that's an extremely powerful formalism. So instead of us struggling with which are the forces at play, you simply have an expression for the potential energy and the kinetic energy. And the kinetic energy is the same always, right? It's just the velocity squared times the mass times a factor of half. So the only complication is if you transfer this one into, let's say, polar coordinates or spherical coordinates. And then the thing we have to label with is actually the potential energy. But sometimes it's easier to find the potential energy than to find the forces. So this is an extremely powerful formalism which you will encounter in many, many physics courses. And this will basically end the semester, and it's going to function as a kind of motivation for what you're going to meet in later physics courses. So think of this course here as a kind of starting point for an adventure in physics. That's the way I want you to look at the final things we're doing here. I also wanted to bring up some of the small things with the midterm. And let me just share with you a figure which was generated by Nathan of what you might expect to see in exercise 1E. So let me show you that here before we move on. So I sneak in some hints and small things about the midterm. And let me see if I can find it here. Oh, perhaps I have too many windows open. Let me just see. It should be there. Sometimes here we are. Those of you which are here can see it, but those of you which are online can probably not see it. So let me see if I can get it up. There we have. So this is it from the Slack page. But this is the exercise 1E. I don't know if you see that well. So the first one up to the left, that is when you have the standard gravitational force. And then you get something which looks like an elliptical motion. This is with the starting conditions or initial conditions which correspond to elliptical motion. And then you get all this kind of beautiful motion, which simply comes from the fact that you're getting some kind of chaotic motion here. You can see there are some, like for r equal 2.6, you can see something which looks like 3 main orbits, and then this repeats itself again and again and again. So clearly, if the Earth and the Sun were to behave like that, I guess dizziness would be the kind of normal state of or normal state, right? So luckily, the Earth doesn't move like that. And then you see also the final one with beta equal to 3. That's the exponent. That is the case, and as we discussed with the analytical solution for that case goes like 1 divided by cosine of an angle. So your radius will actually diverge. And that's what you see. However, what you will also notice when you look at conservation of energy and angular momentum, and remember now that for angular momentum, you don't need to show Kepler's laws. You don't need to calculate the area. The only thing which suffices is actually you taking the cross product of the position with the velocity. And you have these from your calculations as a function of time. And what you will see here, you can't see this, not everybody can see it, but this is 10 to the minus 11, which is the arrow. And this just fluctuates around 0. So that's a perfect conservation of angular momentum. And even for the case when you have, so angular momentum with this type of forces, irrespective of the exponent, has to be conserved. And you see that from the numerics, except that you get some glitches for the last case where you have 1 divided by cosine of an angle, and then the radius can diverge. But for all the other cases, you see that the angular momentum is basically constant as a function of time. So time is on the x-axis. One thing you will notice also, since the radius for the beta equal to 3 can actually diverge, then you will see that when you calculate the potential energy, you may get large values, and they may not give you something which looks numerically stable. But if you look at the results here for the other ones, you will see now that to within the numerical accuracy you're dealing with, these quantities are basically conserved. And so the forces are energy conserving, but the type of orbits you get, which when you look at the top here, they are clearly orbits which would make us pretty dizzy if the Earth was going to move like this around the sun. So the kind of thing you see here is a numerical evidence that the gravitational force most likely goes like 1 over r. And that's what gives stable orbits over time. And that's a neat exercise, but all the forces conserve energy. And that's also useful to see because these are energy conserving forces, as we discussed from the very beginning of the semester. So when you have a force which just depends on the distance, and in particular, if I have a force which depends only on the relative distance between two objects, then that always leads to energy conservation and conservation of angular momentum. And we see that numerically. But whether the orbits make sense or not, compared with experiment, then experiment for us is the fact that we believe the Earth is moving as an ellipse around the sun. And that the orbit is pretty stable. And we can see that from the numerics. I think this is pretty cool. Actually, these drawings, this is something you can bring with you and show your friends at a party. I think this is cool. Yeah. You can cite me on this, actually. Okay. So the thing I wanted to do now is just to steal some minutes on the discussion of wrapping up this with scattering. And I'm going to take a kind of lax attitude in the sense that I will not go through all the details because we're also not going to work with this. But then I want to jump into the Lagrangian formalism. Okay, any questions? So let me take this one away. Just one small thing before I forget it. So the link which NASA had has recently been changed, so I put that in D2L so you can all correct it. And when you want to generate the positions and the velocities of the planets, if you want to run the calculations in Cartesian coordinates in 3 dimensions, when you click on generate ephemeris in the bottom left there, then it will generate the positions and the velocities of the planets at a given time. And you will also see here that it takes the sun as the center of the system. So the sun is not moving. If you let the sun move, as some of you have done, what you're going to see is that the sun barely moves. And that makes sense because it's 1,000 times heavier than Jupiter. The other thing is that it moves less than its own radius. And we have made an approximation in this project that the approximation is that all the objects, all the planets are to be treated as point particles. So we don't take into account the extensions of the objects. So if we were to do that, then life would be much more complicated. So that would be way beyond even a PhD project to deal with that. So we are treating everything as point particles, and we just put the sun as the center of mass, and it doesn't move. And you will see also from the numerics, if you take an average center of mass, you will see that the sun is barely going to move. Okay, so now I'm going to try to wrap up the stuff on scattering. So let me bring up the white book here, the whiteboard. Okay. So let me bring back some of the kind of definitions which we looked at. So this is two-body scattering, 2B scattering, two-body. And what we had was a plane which went through the center of the target. And I'm just writing this in 2 dimensions. So we have the target here. And then we have a projectile or an object which is coming in with a specific velocity. And this is at an infinite distance far away. And then it has only kinetic energy. Now, the distance from this object here and down to the plane, which goes through the center of the target, this distance is called the impact parameter. So this is called B. This is something which we cannot measure experimentally. But we would like, from experimental information, we would like to extract the value of this parameter, because that tells us something about the way the forces between the target and the projectile, how they act and how they behave. Now, when it gets closer, so if we're now looking at the trajectory here, so it's coming in like this, and then it gets deflected, or either up or down. So if it gets deflected up, this means that we have a repulsive force. And if it gets deflected down, it means that we have an attractive force. And let me just mark this with red here. So this will be, and here we have the final velocity, v of f here. So these are vectors. And what we would typically define then, if we now put in a plane here, so we would define an angle between the velocity which we have here infinitely far away and this target. So this angle is normally called theta, and that's called the scattering angle. And that's a quantity which we can measure experimentally. So when you run an experiment, you have a set of detectors, and when something hits the detector at a certain point in the detector, you register what is being hit, you count the number of hits, and you can also extract the angle which it came into the detector. So that's called the scattering angle. Now what we also have is a distance here between the target and the projectile. At a certain point here, we have the minimum distance, and this is called r min. And we would typically also have a radius or a distance between the target and the object here, which we call for r of phi, and this will be the angle phi. Now, what we have analytically, is that we derive this expression here, where we have a constant of 1 plus epsilon multiplied with cosine of phi, if the force is attractive. So this is an attractive force, like the gravitational force, or the gravitational potential, the gravitational force. Alternatively, it could be equal to, or it's given by the same constant, but then we have an epsilon cosine phi minus 1, and then we have a repulsive force. Now, what we would define then is a new angle, this angle phi of m, which is simply defined as the projectile being infinitely far away from the target. Being infinitely far away from target. And if you look into Taylor, we are not going to do the geometry here. So there's going to be an angle phi of m here. It's not exactly this angle, but it's the angle where the target is going to be far away. So you can now think of an object coming in, and then it gets deflected, and then moves away. It can be attracted, or it can be repelled from the target. And then after some time, it's infinitely far away. And what you could think of then is that the object doesn't feel the target, the presence of the target anymore. So this is a typical situation which you would encounter when you run experiments. When you set up your detector, what you're assuming then is that the detector is so far away that the target does not influence the velocity of the projectile which comes in. So it comes in with a velocity. You can think of this being infinitely far away, and it does not feel a target, and then it gets deflected, and then it hits a detector. So these are the basic assumptions when you look at these kind of scattering problems. And it's the basic setup when you run an experiment in particle physics, in nuclear physics, or in solid state physics. And this is often used actually to gain information about the potentials which are at play, or the forces. Because the way it gets deflected and how much is something which will depend on the energy which it has, and it would also depend on the forces at play. So you can gain, by making such experiments, you can gain a lot of information about the physics. Now, this angle phi, which we have, this is a theoretical angle, because that follows from our theoretical calculations. But what you observe in the lab is the angle theta, and that's called a scattering angle. So you can relate these two angles, and if you look into Taylor, I'm not going to go through this geometry, but I'm going to set up the relations between the two angles. And you can, in case you're interested, you can actually see that these angles, so this angle theta is actually given by the absolute value of pi minus 2 times this angle phi of m. So this would be, if you go into Taylor, there is a long discussion of the geometry here. So this is chapter 14.6. And then the other thing which we defined is the total cross-section, which is a quantity you can actually observe experimentally because you're counting the number of objects which hit the detector. So on Monday, we discussed the so-called cross-section, and that's an experimental quantity. And that cross-section is given by an integral over this so-called solid angle. So it's a d sigma of d of omega, and it has an integral over the angles from pi and up to 2 pi, and we're going to have a d of phi, and phi goes from 0 to 2 pi. So this is a phi prime actually. It's not the same phi as the other one. And there's a sine theta of d theta. Now this cross-section, or this quantity which we see here, is called a differential cross-section. And this differential cross-section is normally for central forces. It's independent of the angle phi. So normally this quantity, we can integrate out the angle phi. So that means that what we would get then, we can also, and this is something which I'm just going to give you here as an expression. Can be shown to be given by this impact parameter times the derivative with respect to the impact parameter divided by sine theta of d theta. So I'm not showing this one. This is the kind of laziness which I'm going to do here, in the sense that I'm not going to go through all the mathematical details here. So the quantity which we are interested in and which we can show in from mathematics here, from different manipulations. And I'm going to put these manipulations in the notes if you want to look a little bit closer at it. But we can actually show that this cross-section, this d sigma, when we do the algebra, so it's a little bit convoluted, the calculation, is given by a quantity a, which I'm going to define now, a squared, and this is divided by 4 times sine to the power of 4 of this angle theta half, the scattering angle. This parameter a squared, or this parameter a, actually, is now given by the parameter in front of the force, or the gravitational, or the potential. In our case, it could be a Coulomb potential, and divided by 2 times the energy of the incoming particle. So what we have is that we have a potential V of r, which is typically given in minus alpha divided by r. So if we are looking at a Coulomb type problem, then we are going to have an alpha which is equal to the charges of the 2 particles which are interacting, Q1 and Q2, divided by 4 pi, multiplied by the permittivity in vacuum. You're going to meet this in a course in electromagnetism. So I'm just mentioning it now. If you have the gravitational force, then it's the gravitational constant times the masses of the 2 objects which interact. So this means that what you can do is, so E is the incoming energy of the projectile, incoming energy of projectile. This is a quantity you can establish experimentally. So you know that, you know the velocity of the projectile. Often you can make a beam of particles which is so focalized in velocity. So you can actually have almost monochromatic beams, which means that you have just a beam where all particles basically have the same velocities. It can be a little bit spread out, but you can think of your beam of particles impinging on the target having essentially the same velocity. And this E is the kinetic energy of the incoming projectile. So this is a quantity you can fix in the lab. The other thing which you know is the force. And then you can observe the angle theta. And with the observed angle theta, you can actually construct this d sigma, the omega, where the omega is now the so-called solid angle, as we discussed. So I'm going a little bit fast through these things. I apologize for that, but I just wanted to show the link between what we have been doing in previously, where we have a theoretical value for R. I have skipped all these small intermediate steps, which actually lead to that expression, and I'm going to put them in the lecture notes, so you can actually look up the intermediate steps if you're interested. But we are not going to do any exercises. So I just wanted to have this as an aside, because many of you will meet this when you're doing quantum mechanics or other physics courses. So I hope you can forgive me for jumping a little bit fast here without giving you all the details. So the quantity which you see here has actually a famous name in the literature. And this quantity, which you see here, is called the Rutherford classical cross-section, or differential cross-section. So when you want the full cross-section, what you would do then is actually to integrate from 0 to pi, and then you would integrate this quantity, d sigma d omega, and then you would integrate over sine theta of d theta, and that means that you would simply have to perform an integral here, where you integrate from 0 to pi, and then you have this quantity a squared, which is known. You have a 4 of sine to the power of 4 of theta half, multiplied with sine of theta of d theta. And this is the famous Rutherford classical cross-section. So we are not putting any quantum mechanics here. And this served as one of the many kind of classical results which would break with experiments with quantum mechanical objects. So when people did experiments with different types of particles, they would see deviations from this classical formula. And this deviation is something you can ascribe to quantum mechanical effects. So Rutherford's classical formula functions in many energy domains, but it would break down when you're starting to look at domains where quantum mechanical effects start to play a role, in particular when you have bound states in the system. However, it serves as a very useful result, and you can compare theory with experiment. So remember now that this cross-section sigma is something you can extract from the experiment. You would just simply count the number of projectiles which hit your detector, and then simply do this counting at a given energy. So you have a projectile coming in with a specific energy, and then you simply count how many of these projectiles hit, or particles coming in, hit the detector, and that gives you the cross-section. And then you can compare that with these theoretical quantities. And if you see a deviation, then you have to ask yourself, maybe the forces at play are not the correct ones, or maybe there's something more. And this is actually the way we function as physicists or scientists. We have some formalism, and then we want to compare that with experimental data. So the cross-section is actually a quantity you can extract from experiment. And for those of you who may do internships at EFRIB, and you are working in an experimental group, you're going to hear these things again and again and again. And I can already see somebody nodding their heads here. Yeah, you probably met the cross-section already, right? Good. Okay, so I apologize for being a little bit fast because I want to jump into the last topic so that we have some time to dedicate on a topic which is going to generalize what we have done till now. And I'm going to put extra material in the notes so you can read a little bit more about the derivations here. Okay, so the topic which I wanted to talk about now is the, okay, now seems my iPad just went down here, just coming up again. So the topic which I'm going to discuss now is, as I mentioned, is a topic which is going to generalize what we have done. And you will meet many of these concepts again and again. We are going to be able to derive the equations of motions just using the kinetic energy and the potential energy. And there are going to be some quantities which we need to deal with. And these quantities are quantities which I'm going to write down here for you now. So let's now switch gears a little bit. So I guess everybody can see the screen here. Yep. Okay, so let me switch to the Lagrangian formalism. And this is going to be the final topic for the rest of the semester. So the Lagrangian formalism. And this leads to also what's called the Hamiltonian formalism. There are some basic things here which we need to go through. So the overarching thing is that we can derive the equations of motion from kinetic energy and potential energy. From kinetic energy and the potential energy. So that sounds, to me, that actually when I saw this the first time, that was a kind of hair blower actually. I didn't expect it. And it gives a very elegant formalism. And it leads also for those of you who may be interested in taking the graduate course in classical mechanics, you will typically start with this topic. So this is in a way to bridge the gap between the two courses. And then you move into the Hamiltonian formalism, which is also a very powerful formalism. But there are basically 4 elements which we need. And there are some beautiful lecture notes by Richard Feynman, Nobel Prize winner in physics. And you have the links of those in the slides. One is called the principle of least action. Or you might just call this the principle of laziness. That's another name for it. So this is one thing we need, the principle of least action. Then we need to define something which is called a Lagrangian. And I'm going to give you the definition here, and then we are going to argue why it is given by these terms. So this Lagrangian is often, if we now stay in 1 dimensions, so 1 dim, it is normally a function of position, the velocity in the x direction, and if you're going to more dimensions, we will obviously have x, y, z, the velocity in the x, y, z directions, and time. So it's a function of these, and this is given by the difference between kinetic energy and potential energy. So what I'm going to do now is to take a kind of a top-down approach, and I'm going to give you the definitions. And then in the days which come, the days which we have left, I'm going to try to argue and motivate for why we are using these equations and why we have a Lagrangian which is defined as the kinetic energy minus the potential energy. So now I'm just asking you to accept it, and we are going to use it. Then, from this principle of least action, we can derive something which are called the Euler-Lagrange equations. And these are the equations which are going to give us the equations of motion. So let me set up the Euler-Lagrange equations. And I'm going to give you the 1-dimensional case. So Euler-Lagrange equation. So when we are in 1 dimension, we have only x and the velocity in the x direction. So these equations tell us now that the partial derivative, and I guess most of you now have seen partial derivatives in mathematics courses. So the partial derivative of this Lagrangian with respect to x minus the time derivative of the partial derivative of the velocity is equal to 0. And we are going to derive these equations on Monday, next week. So these equations play an important role because they are going to give us the equations of motion. And then there is an element in calculus which is called variational calculus. And some of you may already have met that in mathematics courses. Probably, and that depends a little bit on the math courses, you may have seen the proof that the shortest distance between 2 points is a straight line. Have you seen the proof of that in a mathematics course? You can actually derive that from this Lagrangian formalism. And we are going to plug that in as an example next week. So sometimes it depends a little bit on the math teachers, they show you that, and sometimes not. But that's the one of the cases where you may have encountered some of these concepts. So how many of you have seen the proof that the shortest distance between 2 points is a straight line? Okay. It depends a little bit on and most likely what has happened is that since you guys have been confined to be at home during COVID, the math courses often took away many of these kind of more interesting topics. So we've noticed that. Okay, but I'm going to show you that as an example next week. And that's an extremely useful thing. And this formalism is extremely powerful. It actually allows you to show that. So these are the kind of 4 ingredients which we need. So I promise you that we're going to do this kind of top-down approach to it. Now I wanted to show you examples. So we are going to take the harmonic oscillator first. This is the simplest case which we are going through the semester. And then from the kinetic energy and from the potential energy, we are going to derive the equation for the acceleration. So instead of setting up the forces, we now have a potential energy and a kinetic energy, and from that, we can derive Newton's equation. When you take a course in quantum mechanics, which will be your next semester, your 5th semester, most likely for most of you, you can actually derive Schrödinger's equation, which is the equation of motion in quantum mechanics instead of Newton's equation, from the potential energy and the kinetic energy. So the formalism is not limited to classical mechanics. It's something you can use in basically all physics problems you encounter, in particular where you have energy conserving forces. Okay, so let's do things by examples so that we can, when we meet on Monday again, then we can go through more of the mathematics which is needed, so like the principle of least action. From that one, we can derive the Euler-Lagrange equation. We're also going to discuss why we write it as k minus v and not k plus v. So now it sounds like some kind of black magic, but I'm just going to use the equation now. And then next week, I'm going to motivate why we define the Lagrangian as a difference between kinetic energy and potential energy. Okay, so let's take an example and use these Euler-Lagrange equations on the harmonic oscillator. So what we have now is a standard harmonic oscillator. Which means that we have in one dimension, so we have a kinetic energy, which is just 1/2 of m of v squared. And then we have a potential energy, which we derived early in the semester, which is simply k times x squared. And when we take the derivative of that quantity with respect to x and put a minus sign, we get the force, which is k times x. So let's now use the Euler-Lagrange equations. Lagrange equations. And that simply say that we have a d of L, the partial derivative, with respect to x, which we need to calculate. And if we take the partial derivative with x, we see now that v does not depend on x. And then we have the potential energy, which has, so the velocity doesn't depend on x here in the expression. And then we have a position in the potential energy term. So if we take the partial derivative there, what we get then, when we put in the equations here, is that this is just given by k times x. That's one term. Now, then, the next thing we need is to take the derivative of the velocity. And when we take the derivative of that one, this is simply, we get a factor of 1/2 because we have v squared. So we get m times v. And the final thing which we need is then to set up d of dt of dl of dv. And since we now have the term here, this means that what we get then, and we assume that the masses do not change with time, so we get m, and then we have a d of dt times v, and that term has a famous name, right? So what do we have there? M times something. Acceleration. Thanks. Great. So this is, maybe that was maybe I'm offending you guys with such a question, right? I just needed to break the monotony here when I just speak too much. That was an offense, actually, to ask such a question to you guys. Okay. So m times a. So these are the equations which we have. And now we have to remember that this Lagrangian is actually, so the Lagrangian is actually k minus v. So it means that when I look at the derivative with respect to x, this is actually equal to 1/2 of m times v squared minus 1/2, as we had, of k times x squared. So what you see now is that I have actually forgotten the minus in front of the potential energy. So that means that actually you have to put a minus in front here. Does that sound reasonable? Because I have defined the Lagrangian as kinetic energy minus potential energy. So when I now collect things, and I do d of L of dx minus, and then I do d of L of dt of dv, and you see now that I have minus k of x minus m times a equal to 0. And when I reorder things, I have m times a, which is the same as m times dx, second derivative of x, and that's equal to minus k times x. And that's the expression which we have seen many times before. So what we have done now is, without having derived the equations for the Euler-Lagrange equations, and also just having defined this Lagrangian, by taking these equations which follow from the principle of laziness or the principle of least action, we can actually derive the equation of motion. Now, when we started this semester, we actually started by analyzing the system and finding the forces. And then we found that for a spring force, it went like minus k times x. And then we had the acceleration, and then we were basically done. So now we can actually start with a much more general starting point, which is the kinetic energy and the potential energy. And often, when you run experiments, or you run, as you've been running simulations, you will often have a form for the potential. So a potential surface or potential which between two objects is something which we often can parameterize from experiment. So a typical experiment which you would use is actually scattering experiments. If you remember one of the exercises we had in the beginning of this, I think it was homework 6, you looked at this Lennard-Jones potential. Do you remember that potential? That had some kind of ugly R dependencies. So this potential is a parameterized potential. With that potential, you can then derive the equations of motion using the Euler-Lagrange formalism, without you knowing properly what the forces are like from the beginning. But somebody gives you a potential, which can be parameterized from experimental data. Okay, so let's take another example. I don't know if you're convinced about this now, or the beauty of it. So I'm going to give you another example, which is the gravitational problem. So if you go into Taylor's textbook in chapter 8, you've probably seen that that textbook does not follow the way which we have taken. They actually start with the Lagrangian formalism in chapter 8, and then they derive the equations which we have been studying. So let's now follow what is done in Taylor in chapter 8 by using what comes in chapter 6 and 7, which are actually the topics for last week's. So let's look at the second example, which is the gravitational two-body problem. So the example 2 here. So what we did in that case is that we had a transformation from x and y, and we went over to r and phi. The kinetic energy in these coordinates is now given by the radial velocity, which we wrote like an r dot, plus a term which is given by the angular velocity. So it had r times the angular velocity, which is this derivative of phi with respect to the angle. And then what we also had is a potential energy, which was simply minus alpha divided by r. So it means that our Lagrangian in this case, L, is simply going to be given by 1/2 of mu of r dot squared plus 1/2 of mu of r of phi dot squared plus the potential, since we had a minus, minus, minus is a plus. So this is the Lagrangian here. This is actually where, if you go into the textbook, this is actually where they start in the textbook in chapter 8. And I know that this has confused some of you, but now we're actually going back there because we want to link with our final stage or the final step here. So we know that this is what we normally call the radial velocity, v of r. And this thing here is the angular velocity, v of phi. So the Lagrangian now is a function of r and v of r. So we have two coordinates, r and phi. If we had x and y, we would have x and y, the velocity in the x direction, the velocity in the y direction, and time, and the position in the y direction. So when we now look at the Euler-Lagrange equation, what we need is a d of L of dr minus d dt. So that's one of the equations of d of L of d v of r equal to 0. And we need also a d of L of d of phi minus d dt of dl of d v of phi. And we also want that one to drive that one to 0. So if you have changed polar coordinates with Cartesian coordinates, the only difference would be x and y, vx and vy. Now, if you then go back to the Lagrangian, if you take a look at that one, what you see is that the Lagrangian does not contain phi, right? So phi itself is not in the equation for the Lagrangian. So it means that the first term, which you see here, this dl d phi, is just 0, right? So if we take the last equation, we are going to see something pretty neat immediately. So let's do that. So let's take the last equation first. So this one is going to be 0. And then what we have is a term which contains a half r times phi theta. So this term which goes like dl of dv phi. This is the same now as the derivative with respect to phi dot. So this is the same as d of L of d phi dot. And if we look at the expression we have for the Lagrangian, it means that what we are going to get then, when we take the derivative, this is going to be equal to mu times r squared times phi dot. Now, dl d phi is equal to 0. So when we collect everything, what we are going to get then is that we're going to have, when we take now the time derivative here, when we look at that term, we should also remind ourselves now that phi, if angular momentum is conserved, this is given by L divided by mu of r squared. So that means that if I plug that in, I'm going to get that dl of d phi is actually given by simply L when I plug it in. And when I then take the time derivative, what I have is that dt of L is equal to 0. And that means that we have 0 torque. So if the angular velocity is proportional with the angular momentum, then we can show immediately here that angular momentum is actually conserved. So we have 0 torque, because there's also no dependence on phi itself. So this is something which we know actually. We know that if we have made this assumption up here, this one, then that simply has to state that the angular momentum, the time derivative, is equal to 0. So this, if angular momentum is conserved, then the equations for the angular part, they just lead to the derivative of the angular momentum being equal to 0. Then we can take the last piece, So when I take now dl of d of r, and this is the final piece we are going to look at, when we take the derivative there, we are going to get mu times r times phi dot squared minus alpha over r squared. And then if I take d of L, this is really the final step, this is going to be equal to mu times r. And then I take the derivative of that quantity of mu of r, and that's the same as mu times r dot. And when I collect everything, what I have is mu times r dot is equal minus alpha divided by r squared plus mu times r times phi dot squared. And these are the equations which we actually derived from Cartesian coordinates to polar coordinates. And that's the equation which we could solve analytically in the case where we have a force which goes like 1 over r squared. So we actually have a formalism now where we can derive the equation of motions without starting from the forces, but we start from a potential energy and we start from the kinetic energy. And this is an extremely powerful formalism which we are going to explore in the next 2 weeks before we end the semester. On Friday, however, we are going to spend basically all time on discussing the second midterm. So then we are not going to lecture, but we are going to have lectures next week on this topic. So I'm stopping the recording, but feel free to hang around, discuss the midterm if there are things which are problematic. Julie will help you which are online, and George and I, we will just float around around here. Okay. So for those of you online, I'm going to